This chapter, I'm going to talk about some basic facts about convex sets and functions in Rn. Let me first present the basic properties of the Euclidean space Rn. Now, we denote by Rn the set of all n tuples of real numbers x equals x1, xn. Here, each xi is a real number for I from 1 to n. Then in Rn, we can define the following operations to make it a linear space. So for x equals x1, xn, and y equals y1, yn, we define the addition of x and y as follows. X plus y is the n tuple of real number given by x1 plus y1, x2 plus y2, so on, xn plus yn. And the scalar multiplication of a real number and an element of Rn is defined as follows. For lambda in R and x equals x1, so on, xn in Rn, lambda x is the following n tuples of real numbers: lambda x1, lambda x2, lambda xn. Okay. Now, in Rn, we can define an inner product to make it an inner product space. So, for x equals x1, xn, and y equals y1, yn, we define the inner product of x and y by the sum of xi times yi, where I runs from 1 to n. And this is just x1 times y1 plus x2 times y2 plus so on plus xn times yn. Okay? Now, from this definition, we can see the following properties of the inner product in Rn. Now, given x equals x1, so on, xn in Rn, and y equals y1, yn in Rn, and g is another element, g1, so on, gn in Rn, we have the following properties. The inner product of x and x is always greater than or equal to 0, and the inner product of x and x is equal to 0 if and only if x is equal to 0. Okay. The second property is the inner product of x and y is equal to the inner product of y and x. Okay. And the third property is the inner product of lambda x and y is equal to lambda times the inner product of x and y. Over here, lambda is a real number. Okay, and the distributive property is also satisfied. That means the inner product of x plus y and g is equal to the inner product of x and g plus the inner product of y and z. Okay. Based on the inner product, we can define the Euclidean norm as follows. For any x equals x1, so on xn in Rn, define the Euclidean norm of x by the square root of the inner product of x and itself. Okay. Now, from this definition, we can see that the Euclidean norm of x is equal to the square root of x1 square plus x2 square plus so on plus xn square. Okay. Now, based on the definition of the Euclidean norm, we can easily prove the following properties. For any x and y in Rn, the norm of x is always greater than or equal to 0. And norm of x is equal to 0 if and only if x is equal to 0. Okay. And the second property is norm of lambda times x is equal to the absolute value of lambda times the norm of x. This is true for any lambda in R. And we can also see that the triangle inequality is satisfied. That is, norm of x plus y is less than or equal to norm of x plus norm of y. Okay, and finally, the Cauchy-Schwarz inequality is satisfied. That means the inner product of x and y is always less than or equal to norm of x times norm of y, and this is true for the absolute value of the inner product of x and y as well. Okay, so in the next section, I'm going to talk about the definition of convex sets and their important properties based on the operations in Rn and also the inner product in Rn as well as the Euclidean norm in Rn.